Welcome, everyone. My name is Sam Tyson, and we are Spartan Solutions Engineering, Inc. And this is our presentation on the design and build of TechSmith headquarters. To start, I'd like to explain a little bit about our team. We're a consulting firm made up of 6 engineers, me, the project manager, Matthew Schwager, the structural engineer, Miles Overall, the transportation engineer, Brady Muldoon, the pavement engineer, Callie McPherson, the hydraulic engineer, and James Kervonen, the environmental engineer. So to start, I'd like to do a little bit of a background on TechSmith and why they came to us for this project. They got together with the MSU Foundation about building a new headquarters because they currently reside in Okemos. As you can see in this picture right here, they are in 4 separate buildings and currently have 300 employees. They do have interns from MSU, and they got a $15 million capital investment from the MSU Foundation for their new headquarters. The design problem statement that the MSU Foundation and TechSmith came to us for was to design a building near MSU campus for their new headquarters. The MSU Foundation allotted them 5 acres of land for construction, and TechSmith believes they need a 62,500 square foot building that gives them the capabilities for 300 employees and for some growth of up to 50 employees. Since COVID has happened, although they are half and half online and half in person, so that allows some flexibility. The allotted land is near the vacant Spartan Village apartments, so that does allow some development to happen in the area in those apartments and put some shops in or anything else. They do want a sustainability aspect to the design. So our team is shooting for a gold LEED rating. And also, since they are a tech company, they are always working together. They would like a employee-focused design. As you can see here, this is an aerial view of the plot of land that was allotted to us in TechSmith to do our designs on. If you look on the left here, you can see where the star is. That's the 5 acres, and on the right is the zoomed in version of that. South Harrison runs north and south where this arrow pointer is, so you can easily see it. And to the south of the plot of land is Crescent Road, and that wraps all the way around. So that gives us 2 access points to the site. If you look to the west of the star, that is the Spartan Village apartments, which are vacant right now. They are far enough away where they don't get in the way of the designs, and we don't have to mess with that. After hearing all this from TechSmith and the MSU Foundation, we have come up with a design that we think best suits the plot of land and the asks of TechSmith. So as you can see on the right side of the screen here, this is our site plan design. The south side of the plot of land is where we decided to build the building. We did design for a green roof and solar panels on top of that, which adds some sustainability aspects. To the north is the parking lot that has 303 spaces. There's actually some space between the building and the parking lot, which allows a spot for parking benches or lunch areas and so on. Our hydraulics engineer has designed for a storm system to go throughout the parking lot and into a detention pond, and then eventually into an existing 30-inch storm sewer that runs north and south of Harrison Road. Our transportation engineer also designed for the access road to go into Crescent Road here and a delivery depot into the TechSmith headquarters that allows some deliveries and anything else that TechSmith orders to go straight into the headquarters without having to go through the parking lot. Along with everything you can see here on the site plan, our environmental engineer has also designed some upgrades to the East Lansing wastewater facility, and he'll go more in depth into that later on in this presentation. So without further ado, I'd like to hand it off to Matt to talk more about the building.
All right, thanks, Sam. My name is Matt Schwager. I am the structural engineer here at Spratan Solutions, and I was in charge of designing the TechSmith headquarters building at the south end of the job site for TechSmith. All right, so our project goals for the structural part of the TechSmith redevelopment is to design a building that met all of the specifications and the needs given to us by TechSmith. And their main focus was a building large enough for 300 employees that they currently have, plus the expansion of up to 50 new employees and student interns coming from Michigan State University. They really wanted to focus on some collaborative spaces for groups of 3 to 4 people to work. So whether that be large open spaces in the middle of the building or more secluded office space around the outsides of the building. Not only did they want space for the team to collaborate, but they also requested that there be space for hotel stations to be set up. And hotel stations are just places where TechSmith employees that normally work remote can come to and work, without any hiccups or having to bring any of their own equipment with them. Or if there's a client or somebody else related to TechSmith that comes into the building for the day or for the week, it is important that they have somewhere that they can work without impeding their progress. And then on the west side of the TechSmith headquarters, there was also a request for a shipping and loading dock to bring in any kind of orders or to send out anything that actually came from the headquarters, whether that be product for the employees or anything else that may be. And then they also really wanted to focus on an indoor-outdoor flow of the building. So a kind of a connection between the interior work or the work that's going on in the inside of the building, as well as any work that can be done outside or just any kind of space out in the on the premise that employees can go to either take a break or eat lunch or anything of that nature. Along with those needs that came directly from TechSmith, they also gave us some requirements. We needed to produce a 62,500 square foot building that we decided to split into two levels. And then in order to incorporate that indoor-outdoor flow, we came up with 2 triangular offsets, one on the southwest end of the building and one on the northeast end of the building. One of which would be a triangular offset on the first floor, and one of which would be a triangular offset on the second floor. The second floor offset would be kind of overhead to an outdoor seating area for the employees on the first floor to eat lunch or anything of that nature. And then the second or the offset on the first floor would then be a patio, walkout patio for the second floor. For the same purposes of potentially, eating lunch or taking a break out there, or even taking work out there in the nice summer days. And then along with those offsets and the size of the building, the clients requested lots of south-facing windows to maximize the amount of natural light coming into the building. That way, lights could be turned down or lights could be turned off just to save electricity or even just, make the employees feel like they're not trapped inside of a building. Another big request from TechSmith is that the building meets a gold LEED certification. And as far as the structural aspects of that go, for us, that just includes solar panels and a green roof. And so solar panels are expected to cover this entire west side of the roof from grid line 6 west. And then the green roof is just going to be here on the east side of the building from column line 6 east. And then this yellow rectangle here is going to be a large skylight over the atrium main entrance of the actual building itself. And then just some mechanical units, some roof access for maintenance, anything of that nature is going to be on the roof of the building. All right, and in order to simplify the design process of the entire building to fit our schedule, we, instead of looking at the entire building, we zoned in on one specific bay of the building. So one of these squares that you can see here. And that allowed us to really break down the analysis of all of the loads and everything that are going to be on that one bay, and then just kind of extrude that out to all of the other bays in the building so that we didn't have to go bay by bay or like section by section to design every little part of it. And then these red ovals here on the screen, all 5 of them, those are lateral resisting braces. So those help to distribute any kind of force coming from the wind, either from the west or the east or the north or south. And so to simplify, we decided to take just one of those braces, this one here on the left side, and we designed that for maximum wind loads coming from the south. And that allowed us to make sure that we had adequate sizing for the X brace that we put there. And the location of these braces is important too, because all of them except for this one here are on the outside of the building. So X brace works just fine. There's not going to be any doorways or anything. And then this one here, there's going to be an X brace here as well, but it doesn't interrupt the flow of anything because again, this is that large atrium that I mentioned before. So there's a staircase here and there's not really need for access from either one of these sides to go through this X brace. So we didn't really have to worry about any doorways or frames or anything like that. So that's kind of why we decided to pick those locations here. And then these braces to help distribute the east-west winds. Those were put also where they are just because X braces worked well there, and we didn't want to have to worry about interfering the flow of any of the patio spaces that the employees would need to walk through, so we didn't have to include doorways or anything like that. All right, lastly here, we have some design constraints that we ran into and just some regulations that we had to abide by while designing the building. The biggest constraint that we ran into was just the actual size of the building. With TechSmith giving us a 62,500 square foot building, that only gives us 31,000 square feet on each floor to work with. And we were trying to take into consideration as much of their requests as possible, whether that be the indoor-outdoor space and the collaboration space. It was tough to fit it all into the building and keeping it sizable enough to have all 300 employees in the building. But then also while designing it, we had to keep in mind the zoning ordinances that we had to abide by. And the first one being Michigan State University zoning ordinance, because Spartan Village is a property of Michigan State. So we had to, that was our first stop when designing the building, to make sure that we were in the bounds of all of the rules and zoning that they had. And then on a larger scale, we had to go through the City of East Lansing zoning as well, because City of East Lansing is the larger governor factor of the lands that we were on. And then prior to any kind of building or any kind of start to groundbreak or anything, we had to apply for a building permit from the City of East Lansing. And that's pretty much all I got for the structural design aspect of the TechSmith headquarters. And I'm going to go ahead and give it on over to Miles, our traffic engineer. Thanks, guys.
Thanks, Matthew. Hello, everyone. I'm Miles. I am the traffic engineer attached to this project, and I'm first going to talk about the traffic impact study for this site. The goal of this traffic impact study was to determine how much an impact the new TechSmith headquarters would have on the current traffic operations between the two intersections. This was done by determining the trip generation distribution for the new site, as well as finding the level of service and queuing for both intersections for all movements and approaches. Next, we take a look at level of service. Level of service can range from A to F, with A being the best possible option and F as the worst, which is failing. Anything D and above is considered acceptable. Optimal, no, but acceptable. In a perfect sense, we want everything operating at an A, but that isn't always realistic. The current operations for both intersections operate at a level of A, with the lowest level of service approach being a D. With build analysis showing that the PM peak traffic will lower the level service for the eastbound left turning approach to a F. Queuing is currently operating at an optimal level, similar to how level of service is. None of the current lane storages will exceed their capacity, which is optimal. Our build analysis shows that if the new site is constructed, the only issue will be the left turning movement at South Crescent and Harrison, as it will exceed the current storage capacity. To alleviate the issues that have been presented, we have come up with 2 recommendations. The first is to install a no left turn sign for the eastbound Crescent Road movement during PM peak hours of 4 to 5 p.m. This will still allow traffic to make right turns, but will force left turning traffic to route all the way to North Crescent to make a left turn. Because of this, more storage space may be needed for the North Crescent intersection. What will have to be done is lane markings will need to be redone, but this will not be as big of an issue because no widening will need to be done. Here is a map of the current site and what it will look like once it's built. Our recommendation is to put a no left turn sign at this location to restrict the left turning movement. While it will allow right turning movement to still operate, it will force all the other cars to turn right and route all the way to North Crescent to make a left turn. This picture shows a current overhead of Crescent Road just west of the North Crescent and Harrison intersection. This shows that if needed, the left turning lane could be extended backwards so that more storage space is given. This would be able to be done by just repainting and no need to widen the road. In summary, 300 additional trips will only have a large effect on the PM peak traffic. Installing a no left turn sign that restricts left turns at this intersections from 4 to 5 p.m. would alleviate this issue. This will then require cars that want to make that movement to go to the north intersection to include a left turn. If the queue size becomes too large because of this, lane markings can be redone with no regard to the geometry, as widening will not be done. Another task of mine for this project was to design the site plan for this build. We recommended 303 parking spaces as it was projected to have 300 trips per day. Along the western edge of this parking lot, you can see that EV parking has been installed. While no infrastructure is currently set up to charge the cars, all the wiring is there if anything needs to be built. There is currently a sidewalk on the eastern edge of the site. Our recommendation is to widen that to allow it to be a mixed use path and to install a bike pad right next to it so that people coming from MSU's campus can either walk or ride their bike without having many issues. Finally, just north of the entrance to the site is our loading dock. This was placed here as it went well with how the structural design of the building was, and so that it did not have to traverse through the rest of the parking lot. In addition to all the non-motorized options in getting to campus, there's also a current CATA bus stop that is just east of our building that allows anyone that needs to use the bus or prefers the bus to be able to get to our site. That's all from me. Thank you guys so much. Now I'm going to pass it on to Brady, our pavement engineer. He's going to talk about the pavement design, and go green.
Hey, thanks, Miles. Hi, I'm Brady Muldoon, and I did the pavement design for this project. So some of our goals for this project was to develop the highest quality and most cost-effective pavement design for South Harrison Road, Crescent Road, as well as the TechSmith parking lot. In order to do this, we had to compare alternatives for the road designs and parking lot designs using a full depth HMA, full depth jointed plain concrete pavement design, HMA overlay, as well as an HMA mill and fill. So to properly assess these roads, I had to look at current road conditions. The image to your left shows South Harrison Road that has alligator cracking due to fatigue, as well as transverse cracking due to thermal distresses. South Harrison Road also has transverse cracking due to thermal distresses. However, comparatively to Michigan roads, Crescent Road is not that bad. The table to my right sums up my findings of South Harrison Road and Crescent Road, as well as the present serviceability index. South Harrison having a PSI rating of 2.9 and Crescent Road having a PSI of 3.4. The PSI scale goes from 1 to 5, with 1 being the absolute worst and needing immediate reconstruction, to 5 being a brand new paved road. As mentioned, the severity of Crescent Road is is low. However, the severity of Harrison Road is at a medium rating. So with the current road conditions being known for South Harrison Road as well as Crescent Road, I was able to estimate traffic for 20 years in the future. This was done using the top right equation as follows to calculate the easels for flexible pavement as well as rigid pavement. Easels being how many passes of an 18,000-pound single axle truck the road can take before it essentially breaks or needs repaving. The equation uses 365 days times the annual average daily traffic. These numbers can be seen in the table to the left, times the directional distribution, times the lane distribution, as well as the percent of commercial trucks the road is going to have, times the truck factor. The truck factor being the equivalent easel loading per commercial truck based on the axle and truck weights. This number is times or multiplied by the growth factor. The growth factor can be seen in the equation below. R being the expected annual growth. I assumed Harrison Road to have a 2% growth rate and Crescent Road to have a 1.5% growth rate. In the growth factor equation, Y is accounting for the design year or 20 years. So with the easel estimation being known for flexible pavement, I was able to use this number in AASHTO 1993 to calculate the various overlay depths, their depths, as well as mill depths for HMA overlay, full depth HMA, and the mill infill design. As seen in table 1, I calculated the overlay depth to be 2.5 inches for South Harrison Road and 2 inches for Crescent Road. In table 2, you can see the various layer depths. Here in table 3, I calculated the mill and fill depth to be 3 inches for Harrison Road and 2 inches for Crescent Road. Using the easel estimation for rigid pavement, I used AASHTO 1986 to calculate the concrete depth for South Harrison Road and Crescent Road that can be seen in table 4. With the layer depths being known, I was able to determine a preliminary cost for each design alternative as well as each road based on a per lane per mile basis. This number was used in a life cycle cost analysis for each alternative to determine the most cost-effective solution. As you can see in table 1, the HMA overlay is the most cost-effective alternative. In this table, the EUAC is the estimated uniform annual cost. In addition, you can see that in table 3, mill and fill design is a close second behind HMA overlay design. Though HMA overlay is the most cost-effective solution, it is, however, not the most practical. This is due to it increasing the vertical layer height of the pavement that goes beyond the current curb height. Therefore, mill and fill is the best alternative as it is both cost-effective and practical. So in addition to determining a cost-effective design alternative for the roads, I was also tasked with designing the pavement cross-section for the parking lot of the TechSmith headquarters. To your right is an image of an MSU detail used on their parking structures. So therefore, this is a pre-approved parking detail that will also be used for the TechSmith parking lot. The TechSmith parking lot, as Miles has mentioned, is approximately 133,000 square feet and contains 303 parking spaces. So in the end, the table to the right shows the various costs of construction for South Harrison Road, Crescent Road, as well as the parking lot. which total to approximately $1 million. The costs accounts for the price of HMA, the pavement markings, the price to cold mill the roads, as well as the excavation that is needed to excavate the parking lot. These costs were based on MDOT 2020 pay items. So to summarize, HMA mill and fill is the preferred design alternative as it is both cost effective and practical. In addition, it can last a design, has a design life of 20 years. Also, the current existing HMA can be recycled into the filling portion of mill and fill to lower the cost. It also aids in, or recycling the HMA also aids in getting the LEED certification. However, mill and fill is not immediately necessary. And if MSU chooses to, they could possibly patch various sections of the roads or use crack sealing. The parking lot, however, is necessary for design and will be used in construction.
Thanks, Brady. I'm Callie McPherson, and I'll be discussing the stormwater management portion of the design process. As a quick overview before diving into the meat of the design, we'll first talk about the goals and constraints of the project. Everything about the Textbeth project has really emphasized sustainability, and stormwater management is no different. Sustainability in stormwater management looks like low impact design elements, or LIDs. LID elements can be as something as modern as green roofs or as common as rain barrels. It really depends on the needs of the project. The stormwater design that emphasizes LID elements was really stressed throughout the entire process. Because this phase of the design process concerns stormwater, all design constraints fall under the purview of the Ingham County Drain Commissioner, or the ICDC. The most heavily regulated features of stormwater management are the more quote unquote traditional elements of the design, the storm sewer and the D or retention pond. A storm sewer needs to be designed to accommodate a 15-minute 10-year storm, or a storm that has a 10% chance of happening that lasts for 15 minutes. A detention pond allows for the catch and release of stormwater runoff at a controlled rate and needs to be able to accommodate a 24-hour, 100-year storm. A retention pond allows for the natural infiltration of stormwater back into the soil, and so needs to accommodate 2 consecutive 100-year, 24-hour storm events. The overall site is divided into 14 total subcatchments, outlined here in pink. Some LID elements are their own subcatchment, such as the southernmost vegetative swale seen down here. Elevation-wise, there's a pretty clear break line in the site right about here. So the northern half of the site drains into a traditional storm sewer and detention pond system, while the southern half of the site is routed through low impact design elements. The primary modeling software used here was EPA SWIM in conjunction with AutoCAD. To begin our discussion of design, I'm going to start with the storm sewer. The northern subcatchments drain into one of 6 junctions where the runoff is carried through the pipe system to the detention pond. The volumetric flow rate of runoff entering the sewer was calculated using the rational method, where Q is the volumetric flow rate, I is the intensity of the given storm event, and A is the area of the subcatchment being drained. C is a land use coefficient that represents the permeability of the area of the subcatchment, and these values are provided by the ICDC. For paved surfaces, that value is 0.95, which is pretty high. From there, that volume of water is used to calculate the necessary size of the conduit pipes, which is done using Manning's equation. Concrete pipes were spec'd for this purpose as they don't rust and are relatively cheap and sturdy. The ICDC also mandates that the velocity of water within these pipes must fall within 3 to 10 feet per second to prevent sedimentation in the pipes, which was taken into consideration when sizing the conduits. This table provides a visual of the final determined conduit radiuses seen here on the left. And as you can see, they all fall within the allowable velocity range. The sewer then drains into the detention pond. A detention pond was chosen in this case for two reasons. One, the volume required for a retention pond was relatively unfeasible due to the other goals of the project. And two, the relatively poor soil quality of the site suggests that infiltration would be a relatively slow process. The detention pond was sized using the rational hydrograph method. Essentially, the pre and post-development volumetric runoff is calculated, and the difference between them is taken to calculate the total volume needed to store the runoff from a 100-year, 24-hour storm. The rational method is again used for this, but the I value is much different as it represents a different storm. From there, the surface area can be calculated using an assumed average depth and side slope and rough shape. What you see here is the detention pond storage curve. As I mentioned before, the outflow from a detention pond is a controlled rate. The ICDC mandates outflow be no greater than 0.15 cubic feet per second per acre, which in this case is about 0.9 cubic feet per second total. The light blue line on this graph represents the inflow over the course of the storm event, in this case modeled after an NRCS Type 2 storm distribution. The dark blue line represents the controlled outflow through a 12-inch pipe that releases into an existing 30-inch storm sewer main that links into MSU's larger stormwater management system. As you can see, outflow is never greater than the maximum allowable outflow. These curves were calculated using the pulse method, which is an extension of the continuity equation seen here. So now that we've discussed the more traditional aspects of the stormwater management design, we can get into the low impact design elements. And again, this was to really focus on sustainability in creating a forward-thinking stormwater management design. So the LID elements that were key to the design of the southern half of the site are the green roof, the bioretention cells, and the southern vegetative swale. There is also a vegetative swale to the north that drains directly into the detention pond, and that was accounted for in terms of sizing for that pond. So the green roof was done in conjunction with the structural design team. The green roof is on the eastern half of the building. And the structural design team allowed for 35 pounds per square foot of loading, which translates to a semi-intensive 5-inch soil system and a 3-inch drainage mat. And again, this green roof drains into the southern vegetative swale. Then on the western side of the building, in between the entrance to the parking lot and the building itself, are 3 bioretention cells, which essentially act as mini rain gardens, where water filters through the soil and then drains off also to the southern vegetative swale. There are 3 bioretention cells and they are each 300 square feet with 6 inches of soil to kind of act as a buffer for that runoff that comes in off the driveway. Now, the vegetative swales are sized similarly to the way that pipes are sized, because the ICDC does also mandate the allowable velocity within a vegetative swale. So the ICDC says that that velocity must be between 1 and 3 feet per second. So again, we size with Manning's equation, but this time for trapezoidal flow. And we size to figure out the bottom width of that vegetative swale. And again, that northern vegetative swale, that drains directly into the detention pond. And the southern vegetative swale is connected via sock pipe to the existing 30-inch stormwater main that connects into MSU's main stormwater system. That's it for me. I'm going to turn it over to James, who will explain the environmental and wastewater design process.
Thanks, Kelly. My name is James Carvenin, and I am responsible for the environmental engineering aspect of this project. This portion of the design planning is in regards to the East Lansing Wastewater Resource Recovery Facility, which services the TechSmith building. So today I'll be walking you through the current design at the facility, as well as the planned upgrades and how the methods chosen help to achieve the desired goals. The goals of the upgrades involve the removal of nitrogen and phosphorus from the influent wastewater to low enough levels that are safe enough for the environment in the effluent, using a process known as nitrification and denitrification. Methane will also be recovered from the process with the use of an anaerobic digester. I will walk through the methods through which these processes occur, as well as walk through the new plant design. Presented here is a flow diagram of the current setup at the East Lansing Wastewater Resource Recovery Facility. As you can see, there are currently 5 different sections of the treatment process, most of which will remain the same. The goal here was to make as little changes to the current plant as possible while still achieving the goals. Shown here are the units or processes that are to be replaced, outlined in red. In the section where the current north and south aeration basins are located is where the reactors, which will carry out nitrification and denitrification, will be placed. In the solids handling portion of the process, the sludge storage is not necessary anymore, as the anaerobic digester will hold all of the waste activated sludge and recover methane. Phosphorus in the form of struvite will also be recovered from the belt presses, which are used for dewatering. I would like to give a brief overview on the nitrification denitrification process and explain why this process was chosen for the removal of nitrogen. Nitrification and denitrification are 2 processes that go hand in hand with one another. During nitrification, the microorganisms within the sludge are able to convert ammonia to nitrite and nitrate. The microorganisms within the aerobic reactor need dissolved oxygen and a retention time of about 4 to 5 hours in order to accomplish their goal, while the denitrification process requires an anoxic environment with no oxygen available. Shown here is a small diagram for visualization of the process. Next is a brief overview of the denitrification process. During the denitrification process, microorganisms known as denitrifiers are able to use the oxygen attached to nitrite and nitrate in the process, breaking apart these molecules and releasing diatomic nitrogen, which is able to leave the process freely, which is shown in the diagram below. Shown here is a general overview of what these processes look like in sequence with one another. During wastewater treatment, it is important to have a stream of recycled sludge from the secondary clarifiers that re-enters the nitrification denitrification process to maximize nitrogen removal. Shown here is the upgraded plant design with the aerobic and anaerobic reactors outlined in red. The area where the largest amount of ammonia is converted to diatomic nitrogen is the large middle box outlined in red. As you can see, there is a recycled stream from the secondary clarifier for more efficient nitrogen removal. Shown here is the anaerobic digestion portion of the design. Anaerobic digestion is a process during which the bacteria break down organic matter, which in turn produces methane. The hydraulic retention time for this process is 25 days, which results in 75% of methane recovered. The methane recovered from the anaerobic digester will also be stored in a gas tank nearby. The methane can later be sold to help power the plant. Here's a brief overview of the regulations regarding effluent nitrogen and phosphorus concentrations. Nitrogen is to be at concentrations less than 5 milligrams per liter, and phosphorus is to be at concentrations less than 1 milligram per liter in the state of Michigan, which this plant design achieves. The result of the effluent concentrations can be seen in the following slides over a 100-day test period. As you can see here, the nitrogen concentration stays at 1.4 milligrams per liter throughout the 100-day time period. The number of days is on the x-axis, and concentration in milligrams per liter is on the y-axis. The black line is the line of interest, as this is the total nitrogen in the effluent. The phosphorus concentration also stays at a constant level of 0.092 milligrams per liter throughout the 100-day time period, which is well below the legal limit. Phosphorus removal is highly attributed to the addition of alum throughout the process. With all this being said, I will now hand it back over to Sam.
Okay, thank you, James. So as you can see here, this is the rough estimate of the project cost that we have came up with. The structure itself is going to be the bulk of this at $16 million, and everything else is separated. I put green roofs, solar panels, and bioretention in one because that's the solar aspects. That'll equal 250,000. The storm system, it'll be also 250,000, and we came up with the parking lot total to be around 500,000. The East Lansing water resource upgrades, since they won't be part of this site plan, but they are separate, was also included in this at 600,000, and landscaping and grading at 100,000. Something I also included in this was the engineering design cost. And anything extra on top of that that we may have missed or forgotten about at a 10% of the total, which equals 1,770,000. That makes the total to be 19 million, almost 19,500,000. So before we could start the construction of this, we had to fill out some permits for regulations. These are all the permits that will be filled out and paid for. A water and sewer connection tap permit, just in case we have to tap into some existing lines that are already there for the building. The Ingham County Grading and Soil Erosion and Sedimentation Control permit for grading and moving all the dirt out. And East Lansing water permit for the building as well. East Lansing building permit. East Lansing paving permit for the parking lot. And a City of East Lansing land use permit, because it is still in East Lansing. That also includes Michigan State campus, and a sign construction permit. And here is the construction schedule that we came up with that would fit this schedule. On the next slide, I have a little bit more of an in-depth schedule so you can see the exact date. So as you can see here, we have planning starting in December 10th and actual construction starting on February 1st, which is just demo, removing landscaping, any trees that need to be removed. And then after that, you start storm sewer and structure foundation in June 1st. We have this project going about a year and a half, 546 days to be exact. Because of Michigan winters and our inability to do construction when it's cold outside and snowing, we have finished the structure framing and exterior by October 30th. And anything after that till the 4th is just interior of the building. We have the project ending and cleaning up June 1st to June 8th. And at that point, it should be open up and ready for TechSmith to move in. Thank you everyone for your attention. That's all we have for today. We wish that we could have done this in person, but since we were unable to, this is the best we could do. I have included all of the engineers' names and emails in case anyone has any questions, comments, concerns. We will always be available through email, and thank you.